Welcome to the presentation of the paper Characterizing and Injecting Faults in Executable Models Specified with fUML. My name is Leonardo Montecchi from the University of Campinas in Brazil, and this is a joint work with Guilherme Wilson dos Santos Lopes, also from the University of Campinas. The context of this paper is in fault injection, which is an established approach to evaluate the dependability of systems, and executable models, which are basically restrictions to UML models, UML diagrams, to enable their execution. In this paper, we investigate the application of fault injection to executable models specified with fUML. We understand, characterize the kinds of faults that can be injected in these models, and then we realize an injection mechanism based on model transformation, and finally we apply the proposed methodology to a simple example in the space domain. Just a little background. Fault injection is defined as the deliberate introduction of faults in a system to evaluate their impact. And it is typically used to understand if fault tolerance mechanisms work as expected, and to evaluate them in the system. Fault injection may be applied at different levels. In the past, it has been applied at physical level, which means, for example, applying radiation or interference. At hardware level, which may mean to short circuit pins of hardware components. At software with software implemented fault injection, and also on models. For example, Modify is a well-known technique for doing fault injection on Simulink models. The idea of applying fault injection on models is that, as everything now related to models, that it allows discovering problems early, so discovering faults in the specification, problems in the specification early in the development of the system. Executable models can be seen as a part of model-driven engineering, or at least related to model-driven engineering. Model-driven engineering is a software development approach which is centered around modeling and the generation of artifacts from this modeling. And in particular, then we talk about structured machine-readable models that can be processed automatically by computers. And in this context, we talk about execution of UML models. There have been several approaches in the past, or multiple approaches in the past, since a long time. For example, UMLP by RAMP, or Executable UML, which is XUML, or now XTUML. And the idea is that also if you execute specification models, you are able to discover faults in the specification earlier, and discover faults that maybe cannot be discovered with formal techniques, with, for example, model checking, and also discover faults that may be connected with data, no? So you are able to simulate the model jointly with data. However, there has been incompatible approaches, no? So there have been multiple approaches for model execution in the past, but with some differences between them, and therefore it has been introduced a standard which is called Foundational UML. So it is a standard for the execution of a subset of UML, which has been defined, released by the Object Management Group, or OMG, with the objective to provide a standardized way to execute formally a part of UML. So this standard is called Semantics of a Foundational Subset for Executable UML models, or Foundational UML, or fUML. It was first introduced in 2011, and then latest version is from this year, from June this year, 2021, and it is version 1.5. And here you can find the specification. Basically, it is a restriction of class diagrams and activity diagrams, so to enable a precise execution of models. So just a quick overview on main elements which are included in fUML. So fUML, as I said, is based on class diagrams and activity diagrams. The main executable element are activities. So when you execute a fUML model, you execute an activity. Activities are composed of actions, with each action representing another behavior. So each action is actually a reference to a method call or to another activity. And actions are connected by control flow elements, so edges, control flow edges, which determine the sequence of these actions, so who comes before and who comes later, and object flow, which determines the flow of information between actions, so how basically input and output parameters flow through these actions, and more specifically through input pins and output pins, which are owned by the action. So these are the main elements. As I said, there are restrictions with respect to what can be done, what can be specified in the complete set of UML models. There is some tool support available, in particular Mocha, which is a plugin of Eclipse Papyrus. So Papyrus permits creating UML models, and so also models which are compliant with fUML, and Mocha, if the model is compliant with fUML, is able to execute it. Here there is an example of an fUML model, an activity in which two values are x and y are summed, so the sum of two values x and y. And we can see the main elements. So we have an activity, which is this diagram, then we have the action, the control flow, the pins, and the object flow, just to have an idea of how an fUML model is organized. And in the simulator, in Mocha, you can see the execution of the diagram, with green elements being the parts that are being executed. And so here you can see, if you were running, doing the execution, you could see which part of the model are executed. So in this paper, we defined a methodology to inject faults in these models specified with fUML, with the idea to allow the analysis of exceptional behavior on fUML models and not just the nominal behavior. So this is an overview of the approach we proposed. So we have a first step in which we define the system model and the fUML model based on class diagram and activity diagrams. Then in a second step, we analyzed the fault injection literature and extracted which are the possible faults that can be introduced in this kind of models. And from this specification, then we can add fault specification in the system model. Then with a model transformation step, takes as input the system model and the specification of faults and generates a modified model, a model with faults being injected. And finally, we execute the model with comparing potentially with a nominal execution, so to see if what is the impact of this fault on the system, and so to see if the system works as expected or not. And here there are some tools that we used in this methodology. So everything inside the Eclipse modeling framework. We use, as I mentioned, Papyrus as diagram editor here. We use Viatra and Extend for the model transformation here, and Mocha for the execution engine here in the execution part. Okay, so the first step was to analyze the faults that can be injected in fUML models. So we, starting from work already existing in the literature on software faults, so faults at software level, we tried to understand how these faults were mapped to fUML models, so which were the corresponding faults, modification in the model corresponding to these software faults, and in particular we, based on the work of Durais et al. In 2006 and Natella et al. 2013, from which we used the taxonomy of faults. Then we, after understanding which are the faults, we defined a way to specify these faults on fUML models, in particular with UML comments. So faults to be injected are specified with UML comments that define the kind of fault, the location, and parameters of the fault. And we do this with an ad hoc language. So we define a simple language that is used inside UML comments to do the specification of faults. So describing the kind of faults, the location, etc., etc. And then we defined the injection procedures, so how the fault can be actually injected, so the steps that should be realized to actually do the injection in the model. So we, for each of the identified faults, we defined the steps. You see here, these two are in English because are in the paper. These others are in Portuguese, are in a technical report of ours, but we have this for all the identified faults. And then, based on these steps here, we did the implementation. So we implemented the injector based on model transformation. So the injector takes as input a fUML model with the annotations of faults on UML comments. And then as output, we produce a modified fUML models which contains the fault or faults injected. The implementation has been done with Viatra and Extend, where Viatra identifies the faults and the patterns, and Extend is used to actually do the transformation. So for each fault, we have a kind of procedure pattern in Viatra and Extend that is used to actually realize the injection. Then the last contribution of this paper is to apply the proposed approach on an example application. So we did not complete an extensive case study, but we exercised kind of a proof of concept on some example models which are based on a real application in the space domain, and in particular the satellite Nanosat CBR2, which is a nanosatellite developed by INPE, the National Institute of Space Research of Brazil. In this link you can find more information on the system. Basically, it is a nanosatellite of the CubeSat family with two units, and it is composed of an onboard computer and some scientific payloads which are actually providing the functionality of the system. We based our work on existing public documents to do the modeling. So we did not have fUML models of the system. We created them based on public documents, and references are in the paper if you are interested. And And in particular, we focused on the Langmuir probe, which is a scientific payload which analyzes, gathers data from the atmosphere and the space around it. A payload related to physics experiment, which basically is gathering data and transmitting it to the onboard computer. So we modeled its behavior with fUML, we injected faults and simulated its execution to see if we could find some problems or the effects of these faults. So we have some models like this of the system. Then we did some injection like this. In this case, we injected the fault in this connection here, in this object flow here. And among the results, we could find that after the injection of some faults, and in particular this one, we could identify a potential loop problem, a potential problem of infinite loop in the system, which could be solved by adding a timeout. So we can see that without this countermeasure and the timeout countermeasure, the injection of fault can have different consequences, and so we get a kind of confidence on the applicability of our approach, even if it's a small example for the moment. So in this paper was a first attempt at applying fault injection on fUML models. We defined this methodology for defining faults and defining the injectors, etc. And we did this example application, which in our opinion revealed the feasibility of the approach, but further evaluation and further development is needed. As a future work, we plan to improve the specification of faults, so maybe with a graphical interface or something more user-friendly instead of just UML comments. We plan to work on revising and extend the classification of faults, and also, of course, mainly now to evaluate the approach with a more extensive case study, potentially in the next satellite of INPE or other projects or with other partners. But one of the challenges in doing this is that the adoption of fUML is actually still limited for what we could see. And so this is one limitation of potential further evaluation. So we would need to find developers and people who are experienced in fUML and that are using it in their projects, which may be not so straightforward. Okay, so this was our paper. Thank you for your attention, and please, if you have some questions or doubts, I will be happy to answer them and to discuss the paper in the session. Thank you.